Good afternoon, everyone. Welcome back. Um, so before we're gonna wrap up talking about trees today, and maybe we'll get into the next topic, which is heaps. And before I get going, I would like to find out if anybody has any questions for me before we get started. Okay, no questions. So a couple of things. Homework number 5, which was extended until this Sunday, is due this Sunday. Okay, it's not going to get extended again. And homework number 6 will go out shortly, probably today at some point. And you'll have about a week to do that homework. That would be the week of May 9th. It'll be due the Sunday, May 9th. And then homework number 7 will go out after that, which will be due the week of finals week. So yet to be determined what homework number 7 is going to be at this point. But homework number 6 will definitely go out. We have a few more topics to cover. We want to finish trees. We want to talk about heaps. There's a few sort algorithms that we have not talked about yet. I was hoping to talk about them this semester. We are going to get to talk about them, namely 3 sort algorithms. One of them is going to be quick sort, one of them is merge sort, and one of them is heap sort. And most likely that's what homework number 7 will be like, but still pending to see how much time we have to cover all of this. In addition to all of that, we also want to talk about graphs. Graphs are really an important part of computer science algorithms, and we do want to spend some time on that. So if I have to sacrifice a little bit of sorting stuff to talk about graphs, then we will probably do that, okay? But right now we're going to finish trees and talk about heaps, and then keep moving on from there. Any questions before I get started? It looks like this class is waning in popularity. We started out the class with about 9 people here, and now we're up to 16, but we're still far from the full complement of everybody who should be here. Now we're up to 18, and people are stumbling in slowly but surely into the class. Okay, if there's no questions, then let me get started. I'm going to take you back to the demo that we were working on. I figured out what the problem was. It was a very simple little problem, but so let me just share my screen with you, and then we'll talk about it. Okay. So we are get rid of this. Okay. So what ended up happening is when we ran the test, it wasn't showing us anything in the class in the trees. And what we were doing is basically trying to traverse the tree and show everything that is being added to the tree. So here I'm adding 100 people to the tree. So let me just do that. And I'm going to comment out this code, which I added yesterday, so that we can show that the delete function is working. But let's just take a look at this and see what essentially, we're going to add a bunch of things to the tree, and we want to see what happens when we do that. So when I see my tree, okay, my tree has 10 items in it. If I traverse it in pre-order, I will get this layout of nodes. And if I traverse it in order, okay, I get this layout of nodes. And if I traverse it in post-order, I get this layout of nodes. So how can I figure out what the tree looks like by looking at these traversals? Oh, and by the way, just in case you were wondering, what was the error that was the problem here? When I went to my tree iterator, okay, and I was seeing if it has a next, I was missing this knot over here, okay? If I get rid of this knot from here and I run this again, we see that there are 10 things in the tree, but we can't see them. because every time it goes to see if there is next, if there is any more any more elements, it'll return false. Okay, because this tree element nodes is empty is false, and therefore it returns a false. This needed to be a none. This tree nodes. So if I do that, and now I run the algorithm, I'm inserting 10 people into the tree, and these are the traversals of the 10 people in the tree. So how can I look at this and say, what is my tree look like? What is my tree look like? Well, if remember that when we are doing a pre-order traversal, so if I have a node, a tree that is like this, forget that it's sorted D, E, F, and G. If I'm traversing it in order, okay, in order traversal, and this is not an in order, if I'm doing a pre-order traversal, remember you visit the root node, okay, visit the root node, you've seen it. Visit the left node, you've seen it. Visit the right node, the left child, C, okay, and then D, and then E, this is pre-order, okay, and then F, and then G. Actually, you know what? Let me just do this so that we can come up with something that actually makes sense. Because in order should come out in order, pre-order should not. So let's go back to the example that we were doing before, which is 25, 15, 35, 10, 20, 30, and 40. So a pre-order traversal of this tree will lead to, remember, you visit the node, then you visit its left child. You keep visiting the left child until you can't, you backtrack, you go to the right child, okay? So this will give me 25, followed by 15, followed by 10, followed by 20, okay? Followed by 35, followed by 30, followed by 40. Okay, that's a pre-order traversal. In order traversal is going to give me 10, 15, 15, 20, 25, 30, 35, and 40. And post order is going to give me visit all of the nodes that are my children and then output me. Okay, so this will give me 10, 20, followed by 15, because I visit 10 and 10 has no children, so now 10 can come out. And when I go visit 15, I haven't visited his right child, 20 has to come out, and then 15 comes out. And then when I go to visit 25, 25 said, I haven't visited all of my right subtree, so I go visit the right subtree, and the right subtree is going to be 30, 40, and then 35 can come out, and then 25 comes out last. Okay, so this is an in order, pre-order, and post-order traversal of this particular tree. And notice that when we look at our traversals, we can actually go back and rebuild the tree out of that, okay? We can go back and rebuild the tree out of this, okay? So when we look at these pre-order traversals of our people that we have in here, each person has an ID, okay? Each person has an ID in this case, okay? And notice that the IDs are numbers, so they're gonna be put like in order. You're gonna see the IDs in order. All of these IDs are coming out in order, okay? So this tells you that, you know, I mean, this is a correctly structured binary search tree, because when you go and look at all of its elements, you find that their keys, when you traverse the tree in order, come out in order, okay? So that's an important find, Okay, but what does this tree look like? What does this tree look like? Okay, a pre-order tree says the first thing that I'm going to see is going to be my root node. Okay, my root node in this case, okay, for this particular tree that we're looking at over here, my root node has an ID of 98,362. Okay, its left child, because I'm going left in this case, is 31,164. And the left child of that is going to be 12,685. Okay, and then the next 12804. Sorry, 804. That's that last node here. Then the next one is a key that has yes.
Are you writing? Because we're not seeing. Yeah, there you go. Thank you.
So that's what this tree looks like so far. 1284, 12804, because we've covered the first three keys in here, right? In the pre-order traversal. And then I have 36, okay? Then I have 36,885, okay? So 36,885 is gonna be somewhere over here, okay? 36,885. And then I have another key in here, which is 91,253. Okay, 91,253. 91,253, because 91 is bigger than 36,885 and it's less than 98. And then the next node is going to be 77,095. 77,095 is going to be here. Okay. And then the next one is 73,663. And 73,663 is going to be here. Okay. And the next one, 71,551 is going to be here. Okay. And then we have a 41. We have 41,650. And 41,650 is going to be the left child of this one. 41,650. And the last one is 99,510, which is going to be here. Okay? This is what this tree looks like. If I traverse it in order, obviously, okay?
Professor, we can't see the tree.
Okay, sorry.
That's okay.
If I'm going to traverse it in order, clearly I'm going to get the keys in the order in which they are in here. 12, 804, 31, okay? And then I got to go all the way down here, 36,885, okay? And then 1284, followed by 31,664, followed by 12,804, followed by 3138. Where did 38 go? Is this supposed to be a 38? 36,885. Okay. And then 41,650, 75, 76, 73, 77, 91, 71, 73, 77, 91, 98, and then 99. So that is the in order traversal. And if I do this in post order traversal, it's going to be 12,804, followed by 41,650, followed by 71,551, followed by 73,663, followed by 77, followed by 91, followed by 36, okay? And then there's 31,664, 99,510, and then 98, 362. So really, if we traverse it and we can verify the layout of the tree. So what is the height of this tree? What is the height of this tree? So if I was to give the height of this tree to be
7, 8.
height of 1, 2, 3, 4, 5, 6, 7. This is all at level 6. This is all at level 7. The height of this tree is 8, the way we're calculating the height. Okay? So this is what we were doing in here in this particular run. It's just basically entering things into a tree and then printing them out according to the order in which they're in. And the other thing that we're doing that I commented out over here, now I'm going to comment it back in, is we're going to go through this and we're going to eliminate one person at a time. Okay? And when we eliminate that node, then we just go through the tree again. So if I do this, basically, it shows that I start out with 10. The next time around, it only has, I'm eliminating the person with the key 15, 476. Okay. So I'm eliminating the one, well, in this case, it's not the same tree because I just ran a different case in here. And then I eliminate another key, and then I eliminate another key. And you notice every time the tree is a little bit smaller. So 7 in this case, now it's only got 6. Now it's only got 5. Now it's only got 4. Now it's only got 3, 2.
Professor, I have a question.
Yes.
So does it eliminate just like any random like keys, or does it eliminate the smallest like key?
I'm going in the order in which I generated the keys. Okay.
Oh,
I have these 10 people that I inserted into the tree. And then I'm just picking, like when I created the 10 people that I want to insert into the tree, I created them in a vector. And then I'm going through one key at a time just to delete them, just to prove that it works. Okay.
oh, okay.
Okay. So I'm just, if you just go back and take a look at this code, what I do in this code is actually very simple. I make an array of people. Okay, which returns to me a person array. Okay, so in my main method in here, I'm creating the people that I want in an array. And then I create a binary search tree and I go through and I insert every person in this array. And then I go through and I delete every person in this array, starting with the 0 entry, then the 1 entry, then the 2 entry. So in the same order in which I inserted them, I'm going to remove them. Okay, so that's what this code does. I have this code out there for you on the website. I have it in 2 flavors. I have it in 2 flavors because we believe in flavorful coding. We have both the recursive version and the non-recursive version. Okay. For your homework assignment, I would like for you to base your homework assignment from the recursive version, okay? Because your homework assignment is going to start with this, okay? And then you're going to add things to this. So for your homework assignment, please start from the recursive version of the binary search tree, okay? And both of them are here and both of them work. I tried them both, so they both work just fine. So please, download them, take a look at them. Everything that is here we have done in class. The only difference is that I fixed that bug that we had yesterday and I added this particular code right here to delete from the driver, just to delete the nodes, the people from the tree, one person at a time. Okay, so that's it as far as the demo of the binary search tree that we have been doing, which has taken us forever to get through. Any questions before I go on? Because there's a few more things about trees that we want to talk about. Anybody have any questions for me?
What will the homework 6 consist of?
Say that again.
What will be the homework 6 like? What will have to do in addition to this?
We are going to talk about that. Now
Okay.
we're going to talk about it.
Okay, no problem. Thank you, Professor.
So the things that you, thank you for that question, Eric. Anybody else have a question for me?
I can better me. I don't know.
I got a quick question. I'm a little bit confused as to like, I guess the general idea or the order of like the three different orders. Because I was thinking like, I understand like the pre-order seems to put the nodes from, I guess, from the first to last in terms of the IDs.
Uh-huh. Not in terms of the IDs, in terms of the order in which we visit nodes. Okay, let's go back and take a look at the tree iterator and look at the three algorithms. Okay, we have in order, pre-order, and post-order. Okay, these are the three algorithms that we have done. Okay, and when we talked about them, we talked about how nodes get visited. So here's the in order. In order, visit everything to the left. And when you have visited the leftmost node of what I have, print out what I have, and then go and visit all the right nodes. Okay, so how does that work? Okay, so on this tree over here, okay, how does that work? Actually, let's pick the tree that is actually make it a little bit easier like this. Okay, let's make this here. Duplicate this page and let's go there and let's do that together. Okay, I just want to make sure that we understand how this is working. Okay, I'm going to show you the call stack. Okay, I'm going to show you the call stack and the recursion and how that looks, and therefore how things get printed out. Okay, so here's my call stack. Okay, and we get called, and in order to do that, okay, we're going to assume that this is the tree that we have. Okay, and we're gonna let's just remove these check marks. Okay, we're going to remove that. So now this is the tree. Okay, and I'm going to start out by calling it with the root. Okay, you start out by calling the thing, the traversal in order by you always start with the root node. So the node in this case for the first call is 25. Okay, the node is 25. Okay.
Okay.
The first thing that I'm going to do is the node null. No, it's not. Okay. Do the in order on its left child. Okay, who's the left child of 25?
15.
15. So I'm going to do a call to n of 15, right? Node of 15. Correct?
Yeah.
And then I go to 15. Is 15 null? No, it's not. Do in order on the left child of 15.
So
Okay.
10.
So now we're in the call stack. We have 3 calls to in order, right? 3 calls to in order. This is the in order stack. And now I call the in order on the left child of 10. What's the left child of 10?
There is none. It's null.
So it's null, right? So I come into the method, the node is null, right? So I return, correct?
Correct.
So if I return, I'm basically going back to where n is equal to 10. Correct?
Yeah.
And since I'm returning here after line 52, because 52 was the line that I used to go to node to the subchild, right?
Yeah, it's a 10, yeah.
So in this case, I am now at line 53 in here, which means I output the node 10. Okay.
You said you added to the tree nodes.
So I added to the tree node. That means it's the next node in the tree node, right? So this is what tree node looks like. It has 10 in it, right?
Yeah.
Correct? And now, what do? After I output it, I go to the right child, right?
Yeah.
So let's go to the right child. The right child of node 10 is null also, right?
Yes.
So now I can just go back because there's nothing to do here. And I'm back at node 10. but I'm done with the right child, right? I've done both the left child of 10 and the right child of 10. So I'm done with this node 10, correct?
Yeah, so the node that we last left off, since after we went all the way to the left and added 10, we stay on that node and see if it has a right child. Okay, see if it has a right
So
child.
the order of what we have done is we went here, we went here, we went there, right?
Yeah,
So this is the order. Okay, we went here, we went down to the null, then
yeah,
we came back to node 10,
yeah,
then we went to the right, then we came back, and now we're going to go back to 15. Okay,
yeah,
that's the order in which we're going. We're going 25, 15, 10, go to the left child of 10, nothing there, come back, output 10, go to the right, nothing to do there, come back to 10, we're done with node 10, now go back to 15.
okay. Can you try like how you go back to 15 after? Because you check for the get right child.
Okay, this arrow over here, arrow 2, 3, 4, 5, 6, 7, okay? All
Yeah,
right, we're good so far? This
Yeah.
is arrow 1.
yeah,
From 12 to 15. It brought me from here to there, right? Arrow number 2 brings me from here to there, right? Arrow number 3 took me from here down to n is equal to null, right?
yeah,
Let me just redraw these slightly differently so that you could see them, because we're going to keep them here. So arrow number 1, arrow number 2, and then arrow number 3, right? Correct? All
yeah,
of these 1, 2, and 3 have all been from line 52 over here. Do you agree with me on that?
yeah,
Okay. So all of these 1, 2, and 3, when they return, they're going to return and continue from line 53.
yeah,
We're good with that?
yeah,
Okay, so let's keep going. I go down to here, n is equal to null. So that's not good, right? So I'm going to go back. That's arrow number 4. Correct?
yeah,
I went back. So if I went back to node 10, it means I am coming back from the call at line 52. So now I'm going to do line 53.
okay,
And if I'm going to do line 53, I'm going to output 10.
yeah,
Okay. And then I'm going to go to line 54, which is going to be 5. Right. And
Yeah.
5 is going to bring me back down to here, right?
yep,
To a new case of null. And that's null is going to go back. And when that goes back, that's 5 going back. That, I mean, that's 4, 5, that's 6 going back. Okay. That's 5 going down. That's 6 going back. Okay. When 6 goes back, it's going back to 10, but it's coming from the call to 54, right? On line 54. Which means when this call is done, since I just visited my right child, I don't have anything else to do in this method. It's done. So
Okay.
n is equal to 10 is going to return back to 15, okay? Which is going to be arrow number 7, okay? So this is going to be 7 going back to here, okay? We're okay so far?
yeah,
Okay, so now I'm back at 15, okay? And I'm coming back from going to visit my left child. So since I'm coming back to visit from visiting my left child, I'll output myself. Okay, so that's 15. And then I'll go to visit my right child. Okay, which basically going to be 8, 9, 10, 11, 12, right? And then it's going to go back to here, 13, and then 14. Okay, so it's the path. If we can redraw this path completely, from scratch in a way that actually looks a little bit more like what we're doing. I'm going to get rid of all of these arrows here. Getting rid of all of these arrows. This is a lot of backtracking here. Okay, so the path that I'm taking, if you follow my path, is it's starting here, goes here, goes here, goes there, comes back here, does the visit, goes here, comes back, goes back, comes here, goes left, returns, goes right, returns, goes here, which then returns there, which then goes here, which then goes there, which then goes to child, which then comes back, which then goes to the right, which then goes back, which then goes back, and then visit here. So we're visiting left, visit the node, go right. Okay, we're done. Go back, and then go back. Okay, you always visit the left as much as possible. When you're done visiting the left, going to the left, you visit the node, and then you go to the right. That's why the order is go left, visit the node. I'm calling this visit the node. In other words, take the value, put it somewhere, and then go right. So go left, visit the node, go right. That's in order. Okay? So continuing with this, 10 is out. I've gone all the way down so we're good with this so far?
Yeah, it makes a bit more clear. I got a little bit more, but it makes a bit more sense.
So we're going left, then we're visiting the node, then we're going right. Okay? So I have gone, so far I've gone here, I've gone here, I've gone here, I've gotten back. Now when you go back, you visit the node. Okay? Because I'm coming back from the left. When you come back from the left on line 52, when you come back from line 52, you always visit the node. We're going to call that line that puts the node into the vector as visiting the node. Okay? Visit the node. Now go right, come back, and now return. Okay? Because after I've visited the left and after I've gone to the left and come back and visited the node, I'm going to go to the right, return. The node has already been visited, right? Because I'm coming back from the right branch from line 54. Now I go back to 15. And since I'm coming back to 15 from his left side, right? I'm coming back to 15 from his visiting his left child. I output 15 now. Okay? Visit the node. Now visit his right child. Okay? So now in the recursion in here, I am at 20. Okay? 20 goes to visit his left child. His left child is null. Right? So he comes back, visits the node, which puts 20 in here, and then he goes to visit the right child. When he goes down to the right child, n is equal to null. Okay, he goes back to 20, but now I'm coming back for visiting 20's right child. Right? Coming back from the right child is the end of the method, right? So I go back to 15. And I'm coming back to 15 from visiting his right child. So I go back to 25. And that's when I visit 25. And then I go to his right child. Okay? I go to the right child of 25. Okay? So what has happened is this has returned, and this has returned. And now we're at 25. We're visiting the node 25. And then we're going to his left child, n is equal to 35, right? When I'm at n is equal to 35, I want to visit his left child. So I'm going to go visit his left child. So now I'm at n is equal to 30. And then I'm going to go to his left child, which is null, right? Which goes back. And since it got back from the left child, I'm going to visit 30. And then I'm going to go to his right child. That's null. I come back from visiting the right child. I'm done with 30. So I go back to his parents. And I'm coming back to that from visiting his left child. So that outputs 35. When you come back from visiting the left child, you always output the node. Okay? And then I go to visit his right child. And he says, go to my left child. There's nobody there. Visit 40. Okay? And then I go to his right child. Nothing there. Come back. I'm coming back from the right child. I'm done. And then I'm done. And I'm coming back from the right child. I'm done. So this is the in order traversal of all of my nodes in my tree. Okay? They came out in order because of the way that I have the go left and go right and visit. Okay, so far? That's in order. If I go back and try to do this in post order or in pre-order, okay, let's duplicate this page. So let's visit these nodes in pre-order. Okay. Pre-order, if you look at the method over here that we have up there, pre-order says visit the node, then visit its left child, then visit its right child. Okay. Visit the node, do the left child, then do the right child. That's the pre-order right here. Visit the node, do the left child, then do the right child. So the call stack in this case, n is 25. As soon as I get to 25, I output it. That's pre-order. Okay, I got to 25, I output it. So now I'm going to go to 15. So n is equal to 15. Go to the left. Okay, n is equal to 10. Go to the, so when I visited 15, I outputted 15. Okay, when I got to 15, first thing I do is output the node, visit it. And then I get to 10, I output 10. Okay, so that's what has happened so far. Then I go to null, right? And there's nothing there. So I go back. I'm coming back from visiting the left child, so I have to go visit the right child. Nothing there. I come back. I'm done. I go back to 15. Okay? When I come back from 15, I go to visit his right child. His right child is 20, so I output 20. I go to visit his left child. Nothing there. Go back. Go visit his right child. Nothing there. Go back. I'm finished visiting the right child. I go back to 15. 15, I visited all of his left side, and I visited all of his right side, so I go back to 25. 25 says, go visit my right child. That's 35. And he says, go to my left child. That's 30. Go here, nothing there. Go back. Go here, nothing there. Go back. Okay. And then since I'm coming back from the right child, I go back to 35 and I say, go visit my right child. 40. Visit my left child, nothing. Visit my right child, nothing. Then go back, go back, go back. Okay, so this is the order in which all of the nodes come out if I do them in pre-order mode. Okay, you visit the node first, and then you, now somebody's calling my fax machine. It's probably one of these spamming calls, phishing calls. Okay, so this is the pre-order. And then if I do this again for post-order,
Wait, I have a question. So for pre-order, as we visit, we outcome the node, right?
When you first get to the node, you look at line 60. When you first get to the node, if it's not null, you visit it. Okay? That's what visiting, the line 60 is the visiting part. Okay? That's when we output the node into the list. Here we output the node in between the left and the right. I visit all my left, I output the node, then I visit all my right. Okay? We're good with that? Does that answer your question?
Yeah, thank you.
Okay. So let's do this. In this case, we want to erase all of these. Actually, that's not the right thing to do. Delete this page. And let's do this now, just duplicate this page. I have too many red arrows there. So erase all of this stuff, and let's do the post order. Now the post order does slightly differently again. I go all to the left, I do everything to the left, I do everything to the right, and then I visit my node. Okay, so if you look at post order, go everything to the left, then do everything to the right, and when you're done with both of those, then output my node. Okay, so left, 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 nothing there. I still don't visit the node. I gotta do the right. I go back. Now I've done everything to the left of 10. I've done everything to the right of 10. So now 10 comes up. Okay? And now I go back to 15. Have I visited everything to the right of 15? No, I have not. So let's go to the right of 15. No. I visit his left. I visit his right. I visit his right. I go back. Now 20, I have looked at everything to the left of 20. I have looked at everything to the right of 20. Now 20 comes up. And now I go back to 15. And now I have visited everything to the left of 15. I have visited everything to the right of 15. So now 15 comes up. And now I go back to 25. Does 25 get visited at this moment? No, because I haven't visited everything to his right. So I'm going to go right. When you go right, then you got to do this one to the left. Go visit everybody to his left, nothing there. Go visit everyone to his right, nothing there. So I visited everything to the left of 30, everything to the right of 30. So now 30 comes out. And now I go back to 25. 25 is still not ready to be visited. 35 is still not ready to be visited because I haven't seen everything to the right of him. So I'm going to go to his right. Okay. Go to his left. Go to his right. Go his right. Okay. I visited everything to the left of 40, everything to the right of 40. So now 40 comes out. And now I go back to 35. And since everything to the left and right of 35 has been visited, I visit 35. And now I go back to 25. Everything to the left of right of 25 has been visited. So 25 comes out. Okay. That's post order. Okay. So each one of them is do everything to the left, do everything to the right, and visit the node. In the case of in order, visiting the node is in between the left and the right. In the pre-order, visit the node first, then do everything to his left, then do everything to his right. In post order, do everything to the left, then do everything to the right, and then visit the node. Okay? Those are the three orders in which we can visit nodes in a binary search tree. Anybody have any questions about that? Because I hope that clarifies how this thing is working. That's how you traverse a binary search tree. So you can, any questions about that before I continue? Okay. So the next question that I have is, the next question that I have is, can you see the fact that if I have a binary search tree and I traverse it in order, the nodes come out sorted? In order means they are coming out in the proper key order. Okay, so you can see that a binary search tree is a useful sorting tool. If I put everything into the binary search tree according to its key value, and then I can traverse the tree in order manner, I get everything out of the tree in the order in which it is sorted. So it is really a sorting mechanism, really. How efficient is the sorting mechanism? Well, first you have to account for putting in the elements into the tree, okay? And that turns out to be a log n based, that turns out to be inserting everything into the tree, input. Input is going to be log n, okay? And traversal is n. So the sort in a binary search tree, sort is an n log n complexity, assuming the tree is reasonably well balanced. Okay, assuming the tree is reasonably well balanced. Okay, and we're going to talk about what it means to be a well balanced tree in a second. Okay, so let's talk a little bit about balance. Okay, well, we've talked about height. Okay, we have talked about height. We said that wherever that was, we had a height. This is a tree of height 8. Okay, the question is this tree balanced? Okay, do you remember what the definition of balance is? Does anybody recall the definition of balanced? Okay, let me remind you.
Had something to do with the heights of the subtrees.
Right. So a tree is balanced if all of the tree, if the tree and all of its subtrees are balanced. Okay? And a balanced tree is a tree that has a difference between the height of its left subtree and the height of its right subtree to not be different than 1. Okay? So if I look at this tree and I look at the height of its left subtree, the height of this tree is 7, right? 1, 2, 3, 4, 5, 6, 7. What's the height of this tree? Is it 7?
Isn't it 1 technically?
It's 1. The height of the right subtree of the root node is 1, and the height of the left subtree is 7. Okay? Meaning absolute value of 7 minus 1 is going to be 6. Okay? That's the height difference between the left subtree and the right subtree. Okay? Any number greater than 1, okay, greater than 1 means tree is not balanced. Not balanced. Okay? I don't want to have any subtree that has a left subtree or a right subtree greater than 1. Okay? So if I look at this subtree, over here, which one shall I take? Let's take this subtree right here. The one that's in orange. Is this subtree balanced?
No, I don't think so.
What's the height of the left subtree of this subtree?
7.
No, the left, no, the one that's highlighted in orange here.
Oh, the height is 3?
The height of the left subtree that is rooted at 71,551.
2.
That the left subtree of that.
Oh,
The tree itself is height 2.
Oh,
But
you
this
mean
is what the
Yeah.
left subtree has a height of 1.
yes,
Okay? The right subtree has a height of what?
0,
Huh?
0.
0 or doesn't
Left
have a,
subtree, height of 1. And what's the right subtree here?
there is none.
There
There's
is none, so its height is
0.
0.
0. Height of 0. The difference between the height of the left subtree and the height of the right subtree is no bigger than 1. Okay? So this subtree is balanced. Correct?
Yes,
This is balanced.
yes.
So
Yeah.
let's take a look at another one. Okay? So we're saying that this one here is balanced. Let's take another subtree. This one. Okay? What's the height of this subtree? The whole subtree.
3,
3. What's the height of the left subtree of this tree?
2,
Left subtree has a height of 2, right? Right subtree
0.
has a height of 0.
And
So
that
is
one
this
is
tree balanced? The difference between the left and the right is 2.
No.
So
No, it's not
not
balanced.
balanced. Okay? So there are a bunch of subtrees in here that could be balanced, right? Tree that is rooted at 99,510 is balanced, right? The tree rooted at 71,551 is balanced. So this tree is balanced, right? This one is balanced. This one is balanced. But the one that's 73,663 is not balanced, right? This one here is balanced. This one here is balanced. Let's take another one right here. This is balanced, right? Because its left subtree is 0, its right subtree is 0. That tree that is rooted there is balanced, correct? But its sister node, 36,885, its sibling node, is not a balanced subtree, right? Are we starting to see the difference now between a balanced and an unbalanced subtree? So we want to say that a tree is balanced if it and all of its subtrees are balanced. Okay, so here's a tree that looks like it could be balanced. Here's a tree that looks like it could be balanced, but is it balanced? I'm going to just use letters A, B, C, D, E, F, and G. So the whole subtree has a height of 1, 2, 3, 4, right? Correct? 1, 2, 3, 4. The height of this subtree, h is equal to 3. The height of this subtree is height is equal to 3. So one could say, at first glance, that the tree rooted at A is balanced because there's no difference in height between its left subtree and its right subtree. The difference in height between them is 0. We agree on that? But that remains the question now, is this tree balanced? Well, we don't know yet because we got to look at all of its subtrees. We got to look at all of the subtrees. So if we find one subtree in this tree that is not balanced, then the tree is not balanced. Okay? So let's take a look at this subtree right here. Is this subtree balanced? Well, to determine if this subtree is balanced, we look at its left height. So the height of its left, okay? Left height is equal to 2. And what is its right height? 0. It has no right subtree. The B has no right subtree. Correct? So therefore, this subtree is not a balanced subtree, which means that the tree is not a balanced tree. If I find if I find one subtree that is not balanced, the tree is not balanced. Why are we so worried about balance? Why do we care about balance? Anybody? Why should we care about balance?
Because it will be easy to do the sort.
It'll be easy to do the sort, okay? If a tree is not balanced, it's going to look like this. Meaning, there are height differences based on which path I take, right? If I go to the right subtree of the root node, I don't have a long ways to go. But if I go to the left subtree of the root node, I could travel all the way down to 41,650, which is buried like 7 levels down in the tree. So it takes me a long time to get there. How many nodes are in this tree? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 nodes in this tree. If I was to create a tree that is balanced with 10 nodes, okay, what it would look like? A tree that is balanced with 10 nodes looks kind of like this. Well, let's make them numbers so that we can count the nodes. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This is a balanced tree with 10 nodes. Notice that the paths to get from the root to any of the leaf nodes are all much shorter than in this tree here. Okay? What is the height of this tree? The height of this tree is 1, 2, 3,
4.
right? It's got a height of 4. And a height of 4, the left subtree of this node, of this root node, this left subtree right here has a height of 3, and this one has a height of 2. So that tree looks like it's balanced, as long as all of its subtrees are balanced. If I take these two subtrees over here, which are the left subtree and the right subtree of the tree rooted at 2, the difference between them is that they're both of height 2, right? If I take the left subtree of 4 and the right subtree of 4, they're both balanced, right? If I take the left subtree of 5 and the right subtree of 5, one is a height of 1 and one is a height of 0, so that's balanced, which means the tree rooted at 5 is balanced, which means the tree rooted at 2 is balanced, right? And all I gotta now look is on the left side, the tree over here, this one and that one have the same height. So the tree rooted at 3 is balanced, which means that whole right subtree of 1 is balanced and the whole left subtree of 1 is balanced, meaning that this tree is balanced. And when a tree is balanced, we have greatly reduced the distance between the root and the furthest away leaf node. And as long as we can do that, it makes traversing the tree much faster. Okay? Because as I go and I get into trees that look like this here path, the path passing through the longest path that I have over here, this path over here, kind of looks like a linear list, right? It looks like a list. So it's an order n to get through it. Not log n, order n to get through it, because I have to go n nodes to get there. Getting to all the nodes in this tree is an order log n operation, because all the nodes are much closer to the roots. So we aspire for trees to be balanced. Now, the order in which I put nodes into a tree determine whether the tree is balanced or not. So the order in which I put nodes into my person tree here generated an unbalanced tree. It'll be nice for me to figure out, how do I get it balanced again? Okay? So the order in which I put things into the tree is very important. I don't have any control in the order in which I put them because I'm going to put things into the tree in whatever order they were given to me. Okay? Now, once I put them into the tree, it would be nice for me to be able to go through and balance the tree. And the question is, how do I balance the tree? Okay? Well, one simple algorithm for balancing the tree. So let's take a tree here. Let's draw a tree that has numeric keys in it, and let's balance it. Okay? So I'm going to draw a tree here. So I have 5, 10, 15, 20, 7, 35, 2, 1, 2, 3, 4, 5, 6, 7. Okay, so this is a tree that I have, and I've inserted the numbers in the order 5, 2, 10, 15, 20, 35, and 7. That's the order in which the keys were entered. Order of insert. So that generated this tree, and this tree is clearly not a well-balanced tree, correct? So how can I fix this problem? Well, one option that I have is to go through the tree and get the in-order traversal. The in-order traversal gives me the nodes in the numerical order that they are, right? 2, 5, 7, 10, 15, 20, and 25. So now I take these and I put them into an array or a vector or whatever, some kind of a sequential thing, right? And then I do a 0, 1, 2, 3, 4, 5, 6. I do a binary search through this. Okay? I do a binary search through this. A binary walk through this in-order traversal. If you remember, a binary walkthrough goes to the middle element first. Okay? Goes to the middle element first, gets 10, and says, that's going to be my root. Everything to the left is going to be the left subtree. Everything to the right is going to be the right subtree. Okay? The whole array was the whole tree. Once I determine the root, I know that everything to its left is smaller, therefore it's going to be part of the left subtree. Everything to the right is going to be the right subtree. Now, if I go look at the left subtree and find the root of that tree, every time I look at a particular portion of the array, the middle element is always going to be my root. So the root of my tree is going to be 10. If I look in the left subtree, what's going to be the root of the left subtree? The root of the left subtree is going to be 5. So I'll put 5 over here. The root of the right subtree is going to be 20. The left child of 5 is 2. The right child of 5 is 7. The left child of 20 is 15. And the right child of 20 is 25. So if I go through my array or my elements, my tree elements that I want to put into my tree, and I traverse them in binary order, in binary search order, we're always going for the middle element being the root of whatever subtree I'm working with, I can transform a non-balanced tree into a balanced tree. Okay, so all that's going to be needed in this is that you insert all the keys into the tree, obtain all the keys out in order, put them into an array, and now walk through the array every single time. Let's do another one. Every single time. Let's do this one a little bit. So I'm going to put in the following keys: 10, 5, 7, 6.
Professor,
Yeah.
can you do it with an even amount of nodes? So like what happened when you have two nodes in the middle? Which one you take to be the root node?
That's a good question. That's what I was going to do this time.
Oh, okay, sorry.
That's a very good question, Eric. So that's 4. Okay, that's 15, 12, 18, 1, 2, 3, 4, 5, 6, 7, and then we'll put one more node, 8. And that is 16. But this tree is not balanced, right? This tree is not balanced. Why is this tree not balanced? Can anybody tell me which part of this tree makes it unbalanced?
The left subtree with the 5 as a root, that make it unbalanced because the left subtree is 0 and the right subtree is 2.
Right. So this tree is not balanced. We can all agree to that, right? So if we obtain these nodes in order traversal, what are we going to get? We're going to get 5, 6, 7. Well, let's not do it this way. Let's do an array. 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to get 5, 6, 7, 10, 12, 15, 16, and 18. That's the in order traversal will give us this, right? We can all agree to that. Which means that these here are 0, 1, 2, 3, 4, 6, 7. And how do we find the middle element of an array? Well, we take the minimum plus the maximum and divide it by 2, right? So the low index plus the high index. So looking at the whole array, 0 plus 7 is 7, divided by 2 is equal to 3 in integer division, so that 10 becomes the root. Okay, let's do this in another color. So 10 becomes the root. All right, left subtree, right subtree. Okay, left subtree, 0 plus 2, 0 plus, so left subtree, 0 plus 2 is equal to 1, divided by 2 is equal to 0, right? Correct? 1 plus 2 is 2, divided by 2 is 1, right? No, sorry. 0 plus 2 is, if only I could do math, that would be so much nicer. 2 divided by 2 is equal to 1. So this is the root of the left subtree. So 6 is here, right? So now let's go to the left subtree of that. So the left subtree of this one, that's the left subtree. 0 plus 0 is 0, divided by 2 is 0. So the left subtree of 6 is 5. Correct? So that's done. The right subtree is between 2 and 2. So 2 plus 2, right, is equal to 4, divided by 2 is equal to 2. So the right subtree of 6 is 7. Okay? So far, so good. Visiting the right subtree here, the first index is 4. So now we're looking at this part over here. So 4 plus 7 is equal to 11, divided by 2 is equal to 5. So this is going to be the node that's going to be here. His left subtree is this one. So 4 plus 4 is equal to 8, divided by 2 is 4. So his left subtree is 12. Right? And if I go visit the right subtree here, that's the right subtree. 6 plus 7 is equal to 13, divided by 2 is 6. So this is going to be the right child of 15, which has no left side, right? There's no left subtree here because there's no more elements there. And then his right subtree is going to be 18. And now I end up with a balanced tree. Again. Okay? So we're going to traverse the tree in the order in which it was in order and get the nodes. And then I'm going to walk through that array in a binary search manner where I'm searching different parts of the array and picking out the next node to be the left subnode or the right subnode. Okay? That's how that is done. Any questions on that? So for your homework assignment,
Professor,
yes,
sorry for interrupting you.
no problem.
There is no way to make the tree balance as we are in the elements, like it's straight from the insert method, or is the same thing? Like as you're adding the element, you need to make it an array, balance it, and then add the item.
So it turns out that for binary search trees, there is nothing that you can do like that. Okay. There are a whole bunch of trees types. We are not going to talk about any of those trees here. Okay. Well, we're going to talk about heaps. That a heap is a kind of a tree. Okay. We're going to talk about heaps, but there are a whole class of trees that are by definition balanced. So when you go to insert into the tree, okay, you then make it balanced as you're inserting it.
But for this kind of trees, we cannot.
So for a binary search tree, okay, for a binary search tree, when, for example, like when you're looking at this subtree over here, when you're looking at this subtree over here, and you say, this is the problem in this tree here, right? That it's not balanced, okay? It turns out that there is a way of doing balancing in a binary search tree as you're inserting, because you go insert it, you find out it's not balanced. And then what you do is you rotate this subtree. If you think about rotating it counterclockwise, making 7 the root, and then 5 and 6 to be the children, you end up in this situation over here.
Oh.
Okay, you end up with 7, 5, and 6, and this is a balanced tree.
Okay.
We're not going to cover this way of doing things. Okay, so you could actually make this as part of your insert operation into the binary search tree. Whereas as you go, I insert the 7, I find out, or the 6, and I find out it's unbalanced. I figure out what rotation do I have to make, and I get a binary search tree that is balanced. Okay, we're not gonna cover this method of doing things here.
Okay, but it's good to know. Thank you.
Okay, there are ways of keeping a balanced search tree balanced as it goes, but the strength of a binary search tree is not in keeping itself balanced. Other trees have that capability. Okay, there are these trees called 2-3 trees, and then there are 2-3-4 trees, and then there's there's all kinds of different trees that keep themselves balanced. If we have a chance to talk about those, we will talk about those. But I really feel like it's much more important for us to talk about the graphs that we need to talk about in this course, rather than talk about balanced trees.
Thank you, Professor.
So, any questions about how to balance a tree? Any questions about how to balance a tree? So we're going to discuss 2 algorithms here. Well, we'll wait until we see if there are any questions about how to balance a search tree, a binary search tree. Traverse it in order, put it into an array, walk through that array in a binary search manner. You got the, you can build your tree as you find the middle element. That's the next node that goes into the tree. Okay, just insert it into the tree. Okay, insert the 10, then insert the 6, then insert the 5, then insert the 7, insert the 15, the 12, 16, 18. You're going to find out that you'll end up with the binary search tree that you have down here on the right, down on the lower right, and that is a binary search tree that is balanced. So the question is, 2 questions. two questions that we want to go through right now. One question is, what is the algorithm for figuring out the height of the tree? Because the height is important for us to figure out whether a tree is balanced or not. We need to be able to measure the height. And we need to be able to find out if a tree is balanced. We need to be able to say, tell me if you are a balanced tree or not. Okay? So we need to understand the algorithm for those two methods. Okay? And the way we're going to do this is we're going to write recursive code in pseudocode now, okay? And then we're going to determine whether that is the right way to do it. So the height algorithm, okay? The height algorithm basically is a method that returns an int, and it's called the height, and then you give it the node that you're going to start at. This is a very simple recursive method, okay? If the node is a null, in other words, there is no node, we're saying return a 0. The height is 0 if there is no node. Okay, your book returns a -1, okay? Which kind of like does not make sense to me, because that's why I do this definition of height. If there is no node, what does it mean to have a height of -1? It's much more likely that a height of 0 is more appropriate, okay? So if else, okay, I want to calculate the left height, okay, which is the height of the nodes that get left child. And I want to calculate the height of the right subtree, which is the height starting at the node that get right child. Okay? Okay, get the right child. Now I've calculated the height of the left subtree. I've calculated the height of the right subtree. Now I can calculate the height of the node that is rooted, of the tree that is rooted at my current node. And that is return the max of left height and right height. That is the algorithm for measuring the height of a tree. So let's walk through an example of that. Okay, that's the end of the else, and that's the end of the method. So if I go back to my tree over here, if I go back to a tree over here that I could make 15, 10, 5, 20, 35, 30, and 33. Okay, that's a binary search tree. So what is the height of this tree when we look at it? Well, the height of this tree is 1, 2, 3, 4. The height of this tree is going to be 5. Okay, so what happens if I call this tree and I say, give me the height of the tree? So clearly the first time around, the node is going to be 15. Okay, so I say, great, go measure my left height. My left height is equal to whatever it is, okay? And then my right height is going to be equal to whatever it is, okay? So left height means I'm going to go measure the height of this tree. So now my node is 10, and I want to calculate the left height and the right height, right? Because that's what I do in that method. And then I say, okay, well, go calculate the height of my left subtree. Okay, so n is equal to 5. Calculate the left height and the right height. Okay, So go down to the left subtree. N is equal to null. That returns a 0, right? That returns a 0. Okay. Oh, and here we have to return it. I made a mistake in here. This is not just return the max of the left height and the right height. It says return the max of the left height, right height, plus 1. Okay, so this returns a 0, okay, to 5. So it says the left height is 0, and it goes to measure the right height, the height of the right subchild of 5, and it returns a 0, right? So now 5 is got the information it needs to measure its own height, and it says my height is the maximum of the left height plus the right height plus 1, which means it returns a 1 to here, meaning that the left height of 10 is 1, right? And now it goes to measure the right height, right? It goes to measure the right height, but the height of the right subchild of 10 is 0, so that's going to return a 0. And it says my height is the max of the left height and the right height plus 1. So this node here returns a height of 2. So it says your height of your left subtree is 2. Okay, and then it goes to measure the right height. Okay, so now that we know the left height of that subtree is 2, we go to measure the right height. So n is equal to 20, left height, right height. Okay, so 20 goes to measure his left height. He gets a 0 back. So he says my left tree is 0. He says go measure the right height. So he goes to node is equal to 35. And 35 measures his left height and his right height. Okay, so when 35 goes to measure his left height, he goes down to node 30, left height and right height. So 30 says his left height is 0, and eventually he'll find out his right height is 1, right? Because 33 figures out his height is 1, right? So 1 is bigger than 0. So that returns a 2 over here. So the left height of 35 is 2. The right height of 32 is 0. And now 2 is greater than 0. So the max of them is 2 plus 1. So this returns a 3. So the right height is 3. Okay. So he says, my height is 3 plus 1. So this returns a 4. And 4 is bigger than 2, so he returns a 4 plus 1, which is a 5. So the height of the tree is 5. Okay? So this is how this algorithm works. That's the height algorithm. Okay? How do I determine if a tree is balanced? How do I determine if the tree is balanced? Well, I clearly need to be able to measure heights. So that's why we did this algorithm first, okay? I'm trying to erase all of this. That's why I'm making this algorithm first. So let's go see tree is balanced, rooted at a particular node, okay? So, so the method is balanced, returns a Boolean, okay? Is balanced, and I pass in a node. Okay, if node, always recursive methods have a end case, return true. A null tree is by definition balanced. True. Okay. Else measure the left height, which is the height of node dot get left child and measure the right height, okay, is height of node dot get right child, okay, and then calculate the difference. The difference is equal to the absolute value of left height minus right height, right? Okay, so far so good. I know the difference between my left subtree and my right subtree. And now I'm gonna left tree balanced is equal to is balanced node.get left child. So find out, I know not only do I need to measure the height of my left subtree, I need to also see if my left subtree and my right subtree are both balanced. Node.get right child. Okay. And now I return from here the following. Okay. If the difference, if diff is less than or equal to 1 and LT balanced and RT is balanced. Okay. So if all of these conditions are true, then my tree is balanced. So this is a recursive algorithm that actually will go through the tree. We know how to measure left height and right height, the difference between them. And now I'm going to actually recursively call my left subtree, ask it if it's balanced, ask my right tree if it's balanced. If any of these trees is not balanced, then we're going to end up percolating a false back up through the chain. Okay, so that essentially is the algorithm for doing is tree balanced? Is it balanced? So for your homework, you're going to need to write the height algorithm. You're going to need to write the is balanced algorithm, and you're going to need to implement the balanced tree algorithm. Okay, so this is pretty straightforward, the height algorithm. The is balanced is a pretty straightforward algorithm. And the balancing the tree action is actually a pretty straightforward algorithm. So we're going to give you the binary search tree. That's going to be the one you're going to start with. It's going to be the recursive version. And you're going to work with it to add those three methods to it. Okay? Height, is balanced, and balance. Each one of these methods has a private method that goes with it that does the recursion. Okay? So pattern it along the insert, find, and remove. I give you the signatures of those methods that you need to create. So that's going to be essentially your homework. 3 methods or 6 methods, 3 times 2. Each one of them has a public and a private method. 3 methods that you have to write and a couple of methods for the driver. It's not really that complicated to do that. Any questions about that? That is going to be your homework number 6. Anybody have a question about that? All right, so let's take attendance and stop the recording for another. Stop sharing the screen. Stop. If there are any questions, please feel free to ask me now. I will put out the homework number 6 out on the Mimir and Blackboard and all of that on tomorrow, probably, or later on today. Any questions?
I don't remember if they like went over the like when I was doing the participation in Zybooks, participation 5, I believe. I don't believe they went over like the whole thing in order, post order thing. Other than like this recording of the class, like is there any other sources that you would say to if you want to better understand, or any advice on to trying to just better understand how the orders go? Because I understand it a bit better, but I feel like
Yeah, it's a little bit of a hard thing to wrap your brain around. I understand, Johnny. Just do a Google. Just Google, you know, binary search tree post order traversal or in order traversal. I'm sure that there are all kinds of videos out there, YouTube videos. If I find any resources like those, I'll put them on the website. Okay.
okay,
I haven't looked, but if you find something, also share it with us on Slack. Okay. Take a look. I'm sure you can find some stuff out there that will explain it a little bit more than what I have done. Okay. And if you find something useful, please put it on Slack.
Okay.
So that others can benefit from it. Anybody else? The last thing that we want to talk about before we say goodbye to trees completely, and at that I'm going to discuss, you know, as if we're flying over at 30,000 feet and looking down at the ground to see the details. We're not going to see much detail here. So we're going to see the 30,000 foot view of a data structure called a trie. Okay. A trie essentially is a form of a tree. Okay.
Are you sharing your screen?
I'm going to share my screen. Yes. So let's share this screen only. So a trie is very useful for text processing, for looking up things. So a trie starts out, okay, with letters. Okay, so if I have the word apple, okay, it will put itself into a tree saying a trie, and the trie looks like this. Okay, if I have the word banana, and always the chain is terminated by a node that says, okay, end of the word. Okay, if I wanted to add the word apply to this trie, notice that apple and apply have a common root in the beginning. APPL, okay, will only require adding a Y node in here saying this is another word. So if I start at the root and I navigate down to a terminator node, okay, I find a complete word. Okay. If I'm looking for all words that start with A, I would have to start at the A and then travel that subtree from A to get all the words that, if I have the word banner, it'll be BANNER. Okay. If I have the word, avocado, it'll be okay. So tries are structured just like a tree, not a binary tree, not a binary search tree. Okay, the tree has n number of children at every node. Like for the root, it could have, as if I have words that start with every letter in the alphabet, I can have 26 children for the root. And under A, there could be thousands of children, right? Because there's thousands of millions of words that start with the letter A, right? So a trie is a very good way to organize things, like for string manipulation, for being able to find Okay, show me all the words that start with BAN. Okay, well, very easy. I just go to BAN in the tree and find out all the children of N are of B followed by A followed by N. All the children of that N will become all the words that start with BAN. There's banana and then there's banner. Okay, this is a try. Okay, your book has a whole section on tries and discusses the insertion and lookup and finding and stuff like that in it. Please take a look at that. I'm not going to spend that much more time in it in class. Okay, it's an interesting data structure. We're not going to do much with it in this class, but it's a very interesting data structure to know about. Okay, any questions before we say goodbye to trees and tries? Okay, so we're going to say goodbye and have a good weekend. I'll see you back over here on Monday. Remember, your homework number 5 is due this Sunday. Homework number 6 will do the following Sunday. And we'll talk about homework number 7 next week or the week after. Okay?
Okay.
We have next week is the 3rd of May. Then that's 2 classes. The 10th of May, we have 2 classes, and then the 17th. So we have 5 classes left. Okay. One of them is a review class. So that leaves us 4 classes. We're going to talk next week on Monday. We're going to talk about heaps. Okay. And then we're going to talk about graphs. And in whatever time we have left, we will talk about the other sorting algorithms. We're running out of time. We may not get to all the sort algorithms as far as homework is concerned, but we will find some time to talk about quicksort and selection and insertions and merge sort and heap sort. But we may not get a time to do homework on it. But I want to spend at least 1 or 2 classes on graphs, because graphs are actually a really, really interesting concept in computer science, and it's good to get an exposure to it. We do have a class that is an upper level course, a 400 level course, which is graph algorithms, and that is a good class for you guys to take. It's actually a very interesting class to take. Any questions?
Oh, I had a quick question. Yeah, this is regarding to, I realized I wanted to ask this question in class, but I couldn't remember it. It's regarding to the what you call it, the internship, the TTP. So like I know the application was due last week Friday, I believe. So like when are we expected to hear back?
Sometime next week is what I would imagine. I don't know for sure, but sometime next week probably. I think they're going to try to do the sorting through the applications this Friday, is what I remember Lawrence saying when he was here with us. And I do believe that makes it possible for us to have the results by next week sometime.
This week sometime. All right. No
So that would be the next step, is if you get selected, then you move on to the next step of trying to match with a company or with an internship at Columbia, or depending on which way you're going. That would be the next phase, is to match, and then that would be the final selection. Okay?
All right, no problem.
All right. Anybody else? If you do an internship, either at Columbia's data science or in the TTP in the industry, you do then qualify to be in the internship course for the fall. Ask me about it again on Monday. We'll talk more about it.
Okay.
Okay. Any other questions? All right, folks. Have a good weekend. I'll see you back over here on Monday.
Take care,
Bye.
Professor. Bye.
Bye.
Have a good day.
You too. Bye.
Have a good weekend.